Great. Good morning, colleagues, and thank you, Yancy, for the introduction. I want to thank the NSTF and ProSet for the invitation to speak here this morning about the 4IR advances in astronomy. So that's the theme I will speak to here. And indeed, we won the team award last year for the special theme award, and we were absolutely delighted with that. So in this talk, I will give a background to what's going on in data intensive astronomy, particularly with MeerKAT and the SKA. And I want to thank, of course, the IDIA partner universities, UCT, UWC, and the University of Pretoria for the ongoing support, as well as the SARAO, the South African Radio Astronomy Observatory. So I will highlight work that IDIA has been doing in this realm. And so I've split up the talk in 5 main themes. I'll first talk about MeerKAT and the Square Kilometre Array, the SKA, just to give a bit of background of where we are in South Africa with that and how the SKA is developing. I'll then show some highlights about data intensive astronomy, which essentially is the modern paradigm in astronomy, where we are inundated with data, technology-driven innovations in science that we have to deal with in a way, and the 4IR technologies are essential in making sense of all these observations. So that's the third theme. I highlight the technologies that we use to enable the science, and also then the direct implication of capacity development in South Africa around those skills and transferable skills, and indeed skills for academia, industry, and society. And then I look forward to the next sort of 5 or 10 years, how the SKA will develop and how these technologies will continue to evolve over the time. So I chose as a title for this presentation, Data Intensive Astronomy with MeerKAT and the SKA. And so the first thing I want to do is to just present MeerKAT, the Karoo Array telescope, and the Square Kilometre Array. And in modern day astronomy, we see a lot of technology-driven innovation, more broadly in science and engineering and technology, but it's really telescopes such as the Southern African Large Telescope, the James Webb Space Telescope, for instance, and of course within South Africa, the MeerKAT and the Square Kilometre Array that are really at the forefront of technology-driven innovation. South Africa, of course, guided by the 1994 White Paper on Science and Technology, and also guided by the geographical advantage of the access to the southern sky, invested in astronomy substantially, initially with the Southern African Large Telescope and subsequently through investments in the Square Kilometre Array. And so astronomy as a discipline is really at the forefront of technology-driven innovation, and it goes 2 ways. So astronomy benefits from that, but also the technology benefits from the demands that the astronomers have on data, be it incredible time resolution to study pulsars or rapidly rotating stars, or incredible sensitivity to probe the deepest edges of the universe. So I think that relation between science and technology is really well captured by the Square Kilometre Array project. So the Square Kilometre Array itself is the world's, or will be the world's, largest radio telescope. And the name is derived from the fact that the aspired collecting area of the telescope. So in this case, you can see the image of the MeerKAT radio telescope with the dishes. So if you take all the collecting area together of all the telescopes, it will add up to 1 square kilometer. And that drives the sensitivity of the telescope. MeerKAT is the precursor to one of the components of the SKA, the mid-frequency component. And this has been in operation since 2018, and it's built and operated by SARAO. And I'll give you some highlights of that. So within the context of the Square Kilometre Array, this is a global intergovernmental organization, the observatory, the SKA Observatory, and it's a partnership currently of 13 member countries, including, or not including yet, but possibly including 3 more prospective member countries. with two telescopes, one in South Africa in the Karoo, which is the SKA mid telescope, the picture I've shown you on the previous slide, and the other one is the SKA low observatory in Australia. And these are separated by technology, by frequency range, if you wish. So the telescopes in South Africa operate at a gigahertz frequency, and the telescope in Australia operates at a slightly lower frequency. But the two can work together, and of course there is a shared sky between Australia and South Africa as well when certain objects are up at a given moment, and so they can work together, but they also complement each other. And within the concept of the SKA Observatory, the headquarters are based in the UK. So this graphic is accurate as of August this year, and it shows you the distribution of the partner countries. It's really a globally represented collaboration. And of course, within Africa, there's the African partner countries as well that have been part of the concept and design from the word go. So in practice, this means there are two components to this telescope, one in South Africa, SKA mid, which ultimately will consist of 197 antennas spread over 120 kilometers baseline, and the frequency range at which these operate is listed here. So the little green arrow on the top left, I'm not sure if you can see my pointer, but the little green arrow on the top left indicates where MeerKAT and the SKA mid will be. That's near Carnarvon in the Karoo. And that's chosen to be far away from any radio frequency interference. So it's a very underdensely populated area of South Africa, which is good for radio astronomy because it's free from any man-made or person-made radio frequency interference. Of course, satellites coming over do affect the signal, and they affect the signal anywhere on the world, so you can't really get away from that. But so basically, MeerKAT is currently in operation. The route from MeerKAT to SKA mid will unfold over the next couple of years, initially with the addition of 14 SKA antennas, and that's a collaboration between South Africa, Germany, and Italy, and ultimately the SKA mid with also additional antennas in African partner countries. So that's called the African VLBI network, or the AVN. The Australian component looks different. So if you look at the bottom right, you see dipole antennas in the ground. That's the low frequency receiver to the SKA. That's close to Geraldton in Western Australia. And the telescope will consist of 512 stations with 256 antennas per station. And again, these combined will become the most sensitive radio telescope in the world. Briefly on the science of the Square Kilometre Array, the international project has a number of science working groups, and they include work like cosmology, the cradle of life, the epoch of reionization, that's the study of the very earliest universe when the first stars turn on and ionize the gas in the universe, all the way to the study of pulsars, rapidly rotating neutron stars, the sun, heliospheric and ionospheric physics. And my own research interest is in transients, exploding stars, supernovae, and how they emit radio emission and what we can learn from that. And I was chair of the International Science Working Group for the SKA on transients for the last 3-4 years. So these are globally connected networks of researchers that aim to do the various kinds of science with the SKA as we do. Right, so this is not something that's come about since yesterday. It's a long-term strategy, starting, of course, from a South African perspective with the science and white paper, the '94 science white paper, and it's evolved over a number of decades now. And this timeline just shows you some of the relevant highlights in that timeline. So the SKA site decision was made, 13 years ago now, in May 2012, where South Africa was awarded the mid-frequency component of the SKA. The MeerKAT antenna, which is the precursor to SKA mid, was inaugurated in July 2018. and has been doing science for the last 7 years already. Quite amazing science. I'll share some highlights. And last year, the first MeerKAT Plus and the SKA mid antennas, so the addition growing towards the SKA, were installed, and the pictures on the right show you those antennas being installed. Now, for completeness, I've also indicated a number of other key points, particularly related to capacity development projects in South Africa around astronomy and data-intensive astronomy. And I'll come back to those a little bit later in a bit more detail. But in the context of IDIA, IDIA was launched 10 years ago to start preparing the South African community for the data intensive astronomy challenge associated with the SKA. Right, so I briefly mentioned that MeerKAT was inaugurated in July 2018. Has been doing science for the last 7 years, and quite amazing science, really transformational in its aspect. It is currently already the world's most sensitive radio telescope, and this will only get better when the SKA comes. So I've just highlighted a number of relevant facts around the around the MeerKAT radio telescope. It's constructed and operated by SAREO, the South African Radio Astronomy Observatory. It's located near Carnarvon in the Northern Cape. It has 64 antennas, and this picture in the background shows you a wonderful view of the core of the MeerKAT telescope array. The longest baselines from the telescope's longest ends is about 8 kilometers. But the real challenge, and why we're talking about this here, are of course the data rates that come from these telescopes. So at present, the data rates, the raw data flow is 2.2 terabits per second coming from the telescopes to the processor side on the side in the Karoo, and then up to 2.5 terabytes per hour to the scientists. So a typical laptop, the one I've got in front of me, it's got about 500 gigabytes of storage. And so you need 5 laptops like the one I have every hour just for the raw data that comes from the telescope. And once you start reducing and analyzing that data volume will blow up at least a factor of 3 or 4 to get the processed data products. So MeerKAT and the SKA really present tremendous data challenges to deal with the observations that are coming. And we need to make sense of those observations in a way that's accessible to the entire research community, from novices, from starting students, all the way to the experts who write the pipelines for some of this analysis. And a measure of the success of this telescope is that as of 2 days ago, there are 526 peer-reviewed papers, many in Nature Astronomy and Science, highlighting the science that have come just from this telescope. And that's a really amazing achievement. And so in acknowledgement of that achievement, the Royal Astronomical Society in the UK in 2023 gave the prestigious Group Achievement Award to the MeerKAT team. And I'll quote their citation: "For a series of spectacular observations in radio astronomy, the highlight being the images of the galactic center," which I'll show in a second, "and the spectacular radial bubbles. In addition, the MeerKAT team has supported the development of science and technology in Africa and stress test technology for the Square Kilometre Array." And that's the key point. We're using MeerKAT as a way to develop the technologies that are needed for the SKA. And so this is a shout out to the MeerKAT team who built and operates this amazing radio telescope. So here is a wonderful picture of the galactic center. So this is the center of the Milky Way as seen at radio frequencies by the MeerKAT telescope. And this is a mosaic of individual pointings. One of the innovations of MeerKAT is that it can view a very wide field of view instantaneously, but this is a combination of multiple pointings around the galactic center, and it really shows the dynamic nature of what goes on there. Images like this were previously unseen. It really required MeerKAT to have the instantaneous sensitivity to see the faint wisps and bubbles that you can see in here. The bubbles are supernova remnants, stars that have exploded and eject material back into the interstellar medium. But at the bright point in the center here, that's where the supermassive black hole resides, at the center of our Milky Way. So this image was really transformational, and it was processed on the ILIFU cloud compute facility by IDIA. Ian Haywood, the first author, expert radio astronomer, processed the data, and this is a great example of the way MeerKAT has transformed radio astronomy already and our views of the galaxy. So that leads me to data intensive astronomy. As I mentioned at the beginning, this is the modern paradigm in observational astronomy. We are data challenged in a sense. We have too much data coming in. The 2.5 terabytes per hour is just an example of what we have currently with MeerKAT, and that, of course, will be much stronger in the future. So this background picture shows you the same picture of the galactic center, but now overlaid on an optical view as well, taken with one of the telescopes in Sutherland. And so in the era of data-intensive astronomy, we have to analyze extremely large and complex astronomical data sets that are generated by these state-of-the-art advanced telescopes or simulations. We can also run simulations of the universe that run up to tremendous volumes. And for this, we require high performance, often cloud-based, but not always, but often cloud-based computing, machine learning techniques, artificial intelligence, new visualization tools, data mining, data fusion. So this picture in the background is an example of data fusion, where you combine the views of the same part of the sky, but from two different telescopes and two different frequency ranges. And so in order to prepare the South African community for the challenges ahead with MeerKAT and SKA, 10 years ago, a number of universities came together to form the Inter-University Institute for Data Intensive Astronomy, working in close collaboration with SAIP. And really the overarching goal of IDIA is to build capacity and expertise in data-intensive research, not just astronomy, but focused on astronomy within the South African university research community, to enable global leadership in MeerKAT science and SKA science, ultimately in preparation for the SKA. So to do that, IDIA established and operates ILIFU, which is a federated cloud compute facility for data-intensive research, not only in astronomy, but also in bioinformatics, and supporting many hundreds of students and researchers in South Africa and globally in data-intensive research. The global aspect is important. We're supporting South African-led projects on MeerKAT, but these are all done in global collaborations ahead of the SKA, of course. Right, so there are two main paradigms. The one is it's all about the data. And so what this graph shows you is an evolution over the last 25 years and looking forward into the next sort of 10 years about the typical data rates for a radio astronomy survey. If you have a survey looking at the deep sky, you want to do cosmology, typically you have 1,500 hours on sky with a telescope, and these are the data rates given. And for scale, I've given the petabyte marker and the exabyte marker as well. So currently we're well above the petabyte range. And this is just for a single survey. So there are many surveys on these telescopes, and I'll give you some rates or indications for what the SKA will ultimately need to store and archive. So it's all about the data, and you can see a steep increase in the data volumes in this. So this initially was very much a big data challenge, not just about archiving, but processing and so on. So the red dots are indicated the MeerKAT, the MeerKAT extension, MeerKAT Plus project, the SKA component, and the ultimate build out to the full SKA as well. And you see this becomes an exabyte data challenge and a rapidly increasing demand for data volumes as well. One thing to take away is that this data revolution is really largely happening on the African continent with the MeerKAT telescope here and the SKA being here. So in order to prepare for that, we needed to do something special. The second paradigm change is a changing sociology of doing radio astronomy. In the past, you would go to a telescope, you would take your data, it fits on your laptop, you would process all your data on the laptop, you would write your paper, and that's it. That cannot be done anymore with these data volumes. Much of the key science by the SKA and much of the key science that's being done by MeerKAT are done by large-scale projects, observing for many years. And this is done by globally connected teams of researchers creating these massive data volumes. And really the point is that leadership in the science and to those teams, go to those teams that can deal efficiently with the data. And it's critical to prepare the community through data intensive science with these precursors like MeerKAT for the challenges ahead. So those are the two main things. And IDIA was launched 10 years ago, not quite 20, 10 years ago. And you see former Minister Pandor there, together with the founding director of IDIA, Professor Russ Taylor, and the vice chancellors of the various university partners, and the then director of SORAO, Bernie Fanaroff, there. And so this has now been going for 10 years. We're about to enter our third 5-year cycle. And of course, we're open to new partners as well within this collaboration. The main themes of IDEA are basically centered on technology, science, and education. So in the technology side, we develop the data-intensive cloud system, visualization tools, and visual analytics for big data, cloud-based execution environments for processing, and visual analytics as well. And the science then is linked to the data-intensive programs on the SKA Pathfinders, and particularly done by postgrad students and postdocs, the emerging researchers, to enable them to develop the skills to be the future leaders for SKA science. We run cloud computing workshops and software resources. We develop pipelines and software tools as well. And in terms of outreach and education, we use the ILIFU cloud for hackathons all across the African continent. And we have a lot of public education and science engagements as well. And I'll unpack that a little bit later. Right, so in terms of the technologies, I want to spend a few words on the ILIFU cloud system that was developed and that's using, and how that's sort of transforming, how that has transformed the way astronomers and emerging researchers in South Africa and around the world are dealing with the data flows from telescopes like MeerKAT. So the enabling technologies in this case is the cloud-based compute for data-intensive research, which is globally accessible for a wide range of users. And I sort of alluded to that previously, but basically, if you're a starting honors student or even a third-year physics student or astronomy student, and you want to work with MeerKAT data, the entry point into the analysis is very easy and straightforward. Of course, we also want to provide a platform for experts to develop pipelines and optimize the data reduction techniques. So there needs to be an environment where all of that can happen. And there needs to be an environment where there can be innovation using AI, not just to do the science, but also using AI to speed up data processing as well, where we can analyze and visualize large complex data sets. And machine learning and AI are very much a part of astronomy. And the point of that is, of course, to open new windows onto the universe, to look at the universe on timescales of make images every second, despite these large data volumes, to process them so that you can make an image of the sky every second, to see what goes on those kind of timescales, which hadn't been done before. So that's a real, allows us to look at the universe in a new way. The background image here is, again, a data fusion of MeerKAT and an optical image from Meerlicht telescope in Sutherland. And again, these data are made with a software tool that IDEA developed, which is very easy to visualize. So the ILIFU cloud infrastructure has over 4,000 processor cores It sits at the data center. The data center sits at ICTS on Main at UCT. We've got 14 petabytes of storage, and that's grown a little bit over the last couple of years, and we need to scale up once the SKA comes along, of course. But the point is that it's connected to the CENRAN internet through the CENRAN links. And we basically pull in data from the MeerKAT archive for processing on this cloud-based platform. It was established in 2016 as in partnership with DERISA and CBio, computational biology, bioinformatics, excuse me. It was set up as an infrastructure for astronomy and bioinformatics as a tier 2 facility. And basically, the learning curve to set this up really helped to shape this. And I've listed the ILIFU funding partners, including NICIs, the DSTI, and the various university partners listed here. What this does effectively is provide a platform for users through a very simple gateway, the IDIA gateway, and I'll show that in a second, where students and researchers can simply log on through a very simple sign-on. So we make use of Sapphire, which is the South African identity registry, and the Educane, which is a single sign-on portal for educational resources. And we have this OpenStack information as a service cluster using SAIP for storage. So this is really the best way to facilitate almost 1,000 users now on this system. And it's designed to maximize how much the users can self-support this. The little QR code gets you to the ILIFU website as well. So we were very proud and very grateful to be awarded the NSTF award last year on the special theme of Fourth Industrial Revolution in South Africa. And in the citation, it's quoted, "For their cutting-edge infrastructure and its management, which facilitates global collaboration in astronomy, empowering researchers to analyze complex science, engineering, and technology data with unprecedented efficiency." And that's really a wonderful acknowledgement. And so this infrastructure really has made a huge change in the way we deal with this kind of data. This is the IDIA Gateway. This is the landing page. If you go to the IDIA Gateway, and you basically, as a researcher, have access to different environments. CART is the visualization tool. The Globus Transfers allows you to move data from one place to another, and I'll say a little bit more about that a little bit later. And it's basically done through a Singularity Docker container setup, so people can come with their software, and as part of containers, you can pull the environment together that you need for the processing. And this is the way that the future SKA regional centers will operate as well. Part of that is also a visualization environment. So on the gateway, you can click on Carta, which is the visualization tool developed by IDEA in partnership with four other partners, excuse me. And here you can visualize your complex data cube. So typically the astronomy data has 2 dimensions, position on the sky, and a 3rd dimension, which is frequency, or even a 4th dimension, which could be time. So you have complex large data cubes, typically terabytes in size, that you want to visualize and analyze. And this can be done on this platform. And the version 5 has just been released, and version 6, which is currently under development, will provide collaborative workspaces for researchers across the world to work on a common data set. And this is now used by thousands of astronomers around the world. It's a replacement for their traditional software tools that we had in astronomy. And we take advantage of modern computational features. This runs and is deployed on cloud-based science SKA regional centers, and it's really a feather in the cap of IDEA in terms of visual analytics tools. Another aspect of visual analytics is immersive data analysis technology in the cloud. So we've released the IDIA project in collaboration with Italy. The INAF is the Italian National Astrophysical Observatory, and we can visualize all these data cubes in 3D or in VR. And really, this is the way the future analysis of these data sets will work. And this is not only for astronomy, you can apply this technology also for other science domains. Imagine a CAT scan in 3 dimensions that you can visualize in this way. In terms of science support, as I mentioned, we're supporting all the South African-led large survey legacy projects on MeerKAT, as well as open-time PI-led projects. And there's a wide range of science that's been done this way. I list here the large survey projects. I led the ThunderKAT project, which again was on transients, and that's been running for 5 years. And really an acknowledgement of the impact of ideas that at least more than a quarter of all the MeerKAT publications, and this is a telescope used by colleagues around the world, acknowledge the use of IDIA and ILIFU for their data processing. I want to speed up because there are a couple of things. I've got about 5 minutes left. So this is just a slide showing some of the science highlights. And really the important aspect of this slide is that this is all work done by master's and PhD students working on MeerKAT. So for instance, the one at the top middle is a beautiful image of a supernova remnant. This was part of the PhD of Kelebohile Khaselawe, and she's published a paper on that this year. And similarly, there are other papers here listed by South African students. The bottom right image shows you an application of AI. Astronomy is a software package developed by Michelle Lochner at the University of the Western Cape, and her student applied this at scale, looking at hundreds of thousands of galaxies to find odd galaxies in this, and this is an example of that work. I won't dwell on this. This is just showing the diversity of projects that we support. On that, not only astronomy, but also bioinformatics from UWC, UCT, Stellenbosch, and the SAMRT as well. Let me just focus then on the capacity development angle and the transferable skills, because that's part of the discussion in this forum as well. How can we make sure that these skills that we develop are more broadly accessible to the community as well? So the aim of IDIA was always to build capacity and expertise in data-intensive research, but part of that, of course, is transferable skills for academia, society, and industry. Now, this IDIA's work in this space doesn't sit in isolation. It is very much part of a consolidated effort across the country, with some initiatives dating back 20 years. So NASP, the National Astrophysics and Space Science Program, has had almost 700 graduates 20 years into its program. It's a network of many universities. SORAO has its own HCD program, and they've awarded over 1,500 scholarships to students and universities across South Africa and the SKA partners. There's the DARA initiative, the Development in Africa with Radio Astronomy, which is a more continental scale project, also with the involvement of South Africa, of course. And then IDIA, as I mentioned, we now supporting 360 astronomy students on ILIFU, and really training students and emerging researchers in federated cloud-based analytics. And we run the hackathons as well. This is just a growth of the number of users on ILIFU. So this is an indication that we're constantly ramping up the number of students onboarded and researchers. The majority are postgraduate students. We have annual reviews of active accounts just to make sure that we manage this in a way that's sustainable. And also, it's the interface of big data and extracting information using machine learning and AI. So this is done. The one on the left shows you the astronomy users, faculty versus staff, and it just indicates that a lot of the users are master students, PhD students from the three partner universities, but of course we are a facility for more than just the three partner universities. The picture on the right shows you within South Africa, about 2/3 of all the users are from South Africa, and they come from all universities. And then there are students from the UK, Netherlands, Japan, Australia, USA, and a whole range of other countries who are also working on the LIFU. This is a little bit of detail. Maybe people can look at this online when the presentation is online to look at the details in the table. I just want to highlight that it includes the first PhD astronomer graduated from the University of Pretoria and the first master's student in astronomy from the University of Venda. So we're really quite broad in our support of astronomy research in South Africa. And this just illustrates the growth in the number of students graduating with expertise in data intensive astronomy. And this really bodes well for the future. The hackathons, we run hackathons, we support that with our infrastructure as well. These are across the continent. We have a strong presence at the African Astronomical Society meeting in Morocco and the General Assembly that was held in Cape Town. And this is really part of what's called the Cascade Outreach model, where we train the trainer across the continent and really reach thousands of people in order to create this environment where we're inspiring the next generation, to the students who are actually working with the MeerKAT data, to the development of the SKA on the continent during the transformational science, and that becomes an ecosystem in which the students can flourish. Right, my time is almost up. In fact, I have 1 minute left, I think, but let me just summarize the forward look towards the SKA era. So we are now having 7 years of science with MeerKAT. MeerKAT will extend with 14 antennas to MeerKAT Plus and eventually to the SKA mid component of the SKA. And with this comes a challenge of scaling up what we're doing at IDIA to the South African SKA Regional Center. The background picture here is a wonderful picture of MeerKAT. Right, so I showed this picture before. This is ongoing development. New antennas are being built on the site to grow more, to expand MeerKAT to become the SKA. And so over the next five years, it's all about the SKA. So we're now in that 2025, 2030 curve, and MeerKAT Plus is coming along. And I've listed here the number of antennas on the scale of where this will be built. And the data rates of these telescopes scale with the number of antenna pairs, the frequency resolution, time resolution. And so for MeerKAT Plus, it will be a few times more in terms of raw data rates. For SKA mid, it will be a factor of 10 more, 20 terabits per second into the correlator, and archiving of order 700 petabytes of data per year. And this is done through a distributed network of data centers around the SKA partnership. I'm almost done, Wilma. So I'll wrap up shortly. So this is where we're moving towards. In South Africa, Sereo appointed the lead for the South African SKA Regional Center, Segopotso Moshapo. And you can see in the model here on the top right, regional nodes, continental nodes for the data, the distribution where the science is being done. And so over the next 5 years, we will continue to support science with MeerKAT, but we will also contribute towards the establishment and growth of the South African SKA Regional Center as we look to scale up complexity of data transfers, along all the themes that are listed here, particularly science platforms, data management, and high performance systems. So just to conclude, I hope I've shown you that MeerKAT is doing an amazing job. And all of that is done and enabled through these 4 IR technologies that have allowed even novice users to work and analyze complex data sets. And the challenge really is now to scale up towards the data rates and volumes of the SKA. With that, I just want to thank the colleagues at IDIA, particularly shout out to Professor Rob Simmons, who designed and implemented the LIFU system, and the various colleagues around the project. this exists within an ecosystem of telescope engineers, scientists, and university support as well. So I want to thank everyone and thank you for your attention. Thanks.